Hey YouTube, how is it going? I hope all is well. Things are not going so great right here right now. I went to start my stream and freaking OBS decided the 20 other times that I've checked it prior that when I go live, it wasn't going to work. So go figure. So yeah, I probably lost half of you, or everybody, which is kind of unfortunate. So, this is going to be our episode 7 of Guitar Amplifier Building Basics, more or less. We're going to have to convert it into that at this point. But what this episode is going to be more or less about is the HT power supply, the resistor, and the caps, and how to select those in order to achieve a particular result. More or less, there is a correlation between the resistor size and the capacitor size that you use that will determine how much ripple attenuation you have, the voltage drop that you get, and the hertz, or the level of attenuation in hertz, I guess if you will, that you decouple from the AC element of the power supply. Sir, and I can see here already that we have no viewers because my other stream died. Go imagine that. It's such a shame. Such a shame. I really tried to do this right, and I biffed it. Well, we're going to try to make the best out of nothing at the moment. But so in other episodes, or several episodes back, I did a series on... well, I didn't do a series. I did a video called... what was it? It was more or less... boutique amp builders, or amp builders, why are they so weird? And it's more or less the whole, what do you call it, death by PowerPoint, what revolved around the idea that having a story is pretty much what you need to have in order to be one of those guys. And it literally just comes down to the whole idea that you need to be a cool character. What the hell is on my hands here? You need to be a cool character. You need to, a lot of things. You need a lot of things. You have to be able to build a killer amp. You have to know somebody. And on top of all that, you still got to be a good businessman, right? That was the whole premise of that thing. And, I kind of beat that one down. Where I'm getting at with that is that I was recently looking around on YouTube earlier today. I should say very recently. And I came across something that came about 5 days ago. So Dave Friedman does a series called Punish Dave with Questions. We'll go to the screen here to check that out. And Mr. DSL here paid $20 to hear this little bit of, well, let's just hear it and see what you think. Let's see if this is going to freaking work or not.
Hey, DSL. What advice would you give to someone starting a small amplifier company?
Make pizzas. Man, I don't know. I good luck.
There's just...
I mean, you might have the greatest thing in the world, but unless it's in this day and age, I don't know. It's probably not the... Don't do it for a full-time job.
Do it for the love of it.
Do it for the love of it, and you make some amps here and there. Okay, fine.
I mean, there are people who are doing it. I mean,
sure. No, it exists. It's just it's a tough business to rely on as your income, shall we say?
And it's just so much competition,
and it's That's why I said open a pizza place.
I don't even know if that would be a great idea.
You're right. Might not be. Burger stand? I don't know.
Yeah.
I don't know about you. But I want my $20 back. I'm not DSL. I didn't pay that $20, but I'd be definitely a little bit disappointed if I paid $20 and that was the advice I'd got. More or less, don't bother, don't try. You're not going to get anywhere. Just make amps for yourself and leave it at that. I kind of feel like Mr. DSL there got raped. Nothing constructive about it. Not even just keep building amps and doing you, and don't Nothing. Just go make pizzas. Thank you for the $20. Go make pizzas. You're never gonna amount to anything. That's what I heard him say. I'd be very disappointed if I was DSL, but as far as constructive criticism would go, like, or not even criticism, just constructive anything, you would think that it would be like, keep making amps. It's really, really difficult. Get them in as many hands as you can. Get on YouTube. Just get the thing out there, and maybe one day you can be like me. But he didn't even get that, and that kind of bummed me out a little bit. So, there's a few of us on YouTube here that are really, really trying to help you as a builder, people who are interested in building these amps, and we give this away for free in essence. I don't ask for anything. I don't want anything from you. So I don't understand why it's so difficult for Mr. Friedman to kind of also help out a little bit. I think he's kind of gotten out of touch, perhaps. We've talked about how he's more or less a businessman more so than an actual engineer anymore. I think at one point he was definitely more involved with that aspect of it. And I don't know. I'm not trying to bash on him just necessarily. That's not the whole point. Where I'm getting at is just the human element of it, I guess. I don't know. I just kind of feel when I see stuff like this, I get a little upset. So anyway, I'm going to kill that screen there, and we're going to move back over, and we're going to talk more about what we're actually here for. So you're seeing a couple things here, but it doesn't really mean all that much to you yet. But more or less all you need to know is that we're taking an AC signal, which looks like this. We're going to convert it via rectification into this. And then with our resistor and capacitor, we're going to smooth it into this. Let's look at a schematic and kind of get an idea of what it is that we're looking at. So if you're not familiar with schematics, this is a good one. It's clean, it's clear, it's concise, and it's pretty easy. It's an 18 watt build. 18 watt, if you've never built an amp before, this is a great one to go with as your first build. It's fun, it's easy, and it does the things. Especially this one here. It's kind of similar to my design in a way. In that it has a parallel triode in the front end of it going straight into the phase inverter. There are some differences from mine to this one, but this one offers single and parallel options, so there's all that. But more or less what we're more worried about is down here. So we have our power transformer here, which basically takes a fixed voltage in at 120 volts and converts it into several different voltages out. Some for heaters, a couple different ones for heaters, in fact. And then the high tension one, or the HT one, which are the ones with all the beans on it, which is the high voltage stuff, the stuff that we really care about. So, as far as rectification goes, we're not really concerned at the moment with what kind. Whether it be tube or solid state rectification, they both do the same thing. They both basically do it the same way. One has a limitation that the other one doesn't, and one of them has a cool factor that the other one doesn't, okay? So for now, we're not going to worry about full wave or half wave or anything like that. Everything that we're going to talk about today is full wave rectification because 99.99% of guitar amplifiers out there use full wave rectification. So that's all you need to know. So going back to our thing here, the rectifier takes the high voltage incoming signal that comes from this point right here, these red that you see here on either side of the rectifier, takes this and converts it into this. So what it does is it takes the negative going signal, so if you imagine this goes up X amount of volts, swings back down through 0, so this is 0 volts here, reference, down to some negative number that's equal to the positive, and then back up again and repeats. Then you end up with this, which looks like a sawtooth or something like that. This is no bueno right here. We can't do anything with this. This is not DC. This sounds like brrr. You would never be able to make an amp work with this. Mainly because the voltage would pretty much disappear and go away anyway. You'd lose half of your peak voltage, more or less. The RMS is what you end up with. Well, what the resistor and the capacitor does is convert this into this. The more capacitance you have, the more it wants to stay up and become a straight solid line like that there, right? Objectively, that's what you're trying to do. This guy right here, this very first capacitor, forget about this guy right now. That's a safety resistor. It has a different function. This guy here is meant to bleed off all the voltage that's stored into these guys away to ground, so that way you can get your grimy fingers inside of the amp. So we're not really worried about that. Also, do please feel free to post stuff in the questions. I see you there, Audio 9. Thank you. I wish I didn't biff my earlier screen or stream, but whatever. We're gonna roll through it. Hold on, let me take a quick sippy. So, we're not worried about this guy. This guy right here is our reservoir capacitor. This is the one that stores the majority of the energy to help make this go from that, sawtooth thing into what looks like this, which we call ripple. This is the ripple that we would hear. And you can just kind of see what it does. So as the voltage goes away or runs away from it, the capacitor discharges, trying to help the remainder of the power supply keep up with it. Well, it can only do so much. And there's a thing that we need in order to make that happen, and that thing is a little bit of resistance in order to resist the current flow. So we need something to help retain that energy and keep it in this area here, right? And then the capacitance, of course, to help maintain the voltage over time. So that's what this guy does. That's what these guys here do. And here's a more pretty looking thing to kind of show you what it looks like. So obviously this here is not ideal. We want it to be like a battery. So you've probably heard of the term B+ as it relates to the HT rail. So HT stands for high tension or high voltage. The B+ refers to the days of yore when radios and other amplifiers that were tube powered, of course, at that era, ran off of batteries. They literally used a battery to power the amp. These are a DC operating, device. So there is that. Now, let's talk a little bit about design criterion. What is the goal of the rectification, but the capacitor and resistor? We talked about how it's meant to get the ripple down and manage the voltage drop over that resistor and deal with the hertz or its separation from AC to DC or whatever. Well, the resistor determines the amount of voltage drop that you have, and it also sets the corner frequency in conjunction with the size of the capacitor that you use, that low cutoff point. This guy right here will help you determine that. Now, what are we looking for, relatively speaking? Objectively, we want to get as close to 0 hertz as we can get. If we can get to 0 hertz or very, very close to 0 hertz, we know that we are fully decoupled, or we have fully decoupled the AC element of our HT from the amp, right? Or out of the amp. That's how you can think of that. Now, the attenuation is more of a criterion that you can use to factor the noise floor, I guess, if you will. So most noise floors, as far as we're concerned, is right around minus 70 dB. So that is probably the lowest number that you should shoot for in terms of relative attenuation for your ripple. But this stacks, this adds up. So the more nodes you have, the more attenuation you have. If you look in here, you'll notice that we have an A and a C. They skipped over the B, but the B node is the screens in this amplifier here. So there are 3 nodes inside of this amplifier. The more nodes you have, the more attenuation you will stack up. Make sense? So if you have 3 nodes of amplification that all have 35 dB of attenuation, 35, 35, 70, you'd end up with like 105 dB of attenuation. That's what you need to know for that. I'm going to take another sip. So, in theory, it would only take about 2 nodes with this level of attenuation to reach that goal. Now, if you can get lower, that's even better. But once you get down to that point, the noise floor, or at least the attenuation of the ripple, is so low that it is below the noise floor. All right. The next thing to take into consideration is the voltage drop. So this resistor here creates a voltage drop, and as you can see here, we've got 360 volts on this node, the A node, and 335 volts on the B node. So there's about a 25 volt difference right there. Does that add up? It about adds up. 25 volts of difference. And you can see here, I kind of went ahead and did some other stuff. So we have a 2.2K resistor with a 33 UF capacitor, and I've already factored out what the likely current is for that portion of the amp. So the B node holds about 12 milliamps worth of current on it. Now, when I say current, I mean current draw. So the screens actually do pull current. There is, signal flow through them, if you will. And they pull more current than the 12AX7s. Now, a 12AX7 pulls about 1 milliamp each. A 12AU7 pulls, I think, 3 times as much. So it's like 3 or 4 milliamps or something like that. Excuse me, I kind of got a burp almost. Yeah, get the beer burps now. As always, have your drink of choice in front of you at all times. I apologize. I know I'm not very funny on this one today. I kind of got straight into the nitty gritty stuff earlier, but I was really just disappointed in my start of this show, which is unfortunate. But in either case, 12AT7s draw a little bit less than 12AU7s. 12AY7s draw a little bit, each one of them draws a different amount. But since the most common tube that is used in an amplifier is a 12AX7, they draw about 1 milliamp. So we know that these draw 1 milliamp each. And then you can use this calculator here to kind of, reverse engineer, if you will, what the actual DC current draw is. In this case here, it's about 26.4 if we have 12 milliamps of current. So it's maybe closer to 11.8 or something like that. Who knows? But you can see here that we have nearly 35 dB of attenuation on the ripple, and our low cutoff frequency is about 2.19 hertz. That's very, very low. That's not bad at all, especially for your first stage of attenuation or filtering. Objectively, you'd like to be a little bit higher, and you could go higher, or lower, that is, if you wanted. So once you get past this first reservoir stage here, with a tube rectifier, you can go as high as you want after that point. You're only really concerned about this first capacitor or reservoir cap, as they call it, when it relates to a tube rectifier. So now we're going to start getting into the design, criterion and goals and limitations and stuff. I like tube rectification. I like the soft start that they have. I just like the glowing glass. I like the way they react. They're kind of reactive, right? They sag a little bit. They have a feel to them. So other people feel the other way. Some people like solid state rectification, which is more immediate and less forgiving, I guess, if you will. So it's stouter. It's more firm. All that fun stuff. It doesn't sag and stuff like that. So different strokes for different folks. But if you're going to use a tube rectifier, there are a few things you need to know. And one of those limitations is the amount of capacitance that you can have on the first node or on the reservoir cap. The range is pretty small. So you can go as low as you want, although going lower doesn't help you at all. But there's a limit to how high you can go on that size. 33 is about as high as you can get away with on an EZ81. I'd say that 33 is about as low as I would. No, let me rephrase that. 30 is about as low as I would go on the first node in terms of that aspect of it, right? So if you are going to go with tube rectification, do not go any lower than 30 UF if your tube allows to go that high. Most all of them do. And the upper limit is usually around 50 or 60 UF, and you don't often see that value. Generally, the highest value you come across is like 50 UF, something like that. Most large bottle versions will take that. Your GZ34, I think you can get away with a 50 UF. I usually run 47 because I don't want to push my luck with them. I think that's why some of these tube rectifiers are prone to failure, is that the builder designs too close to the design limitations of that tube or whatnot, and it can cause problems. Just because Fender and some of these other companies out there may have done it doesn't mean you should do it. Just because you can doesn't mean you should. Now, so the cool factor of a tube differs in respects to that of a solid state. As we mentioned, it has zero give, it's very immediate, it's faster, etc., etc., right? Well, there is no limit, realistically speaking, to the size of the capacitor that you can use first in line, the reservoir cap that you can use for a solid state rectifier. Which is to say that if you wanted to go with 100 UF, you could. If you wanted to go with 200, you could. If you wanted to go with 1,000 UF, you could. 2,000's probably the upper limit. I wouldn't go that high. That's a little ridiculous. The other thing is, too, is that you start getting into ridiculousness in terms of the size of the cap itself. I mean, a 2,000 UF cap that can handle 400 plus volts, 500 volts, 600 volts, it's going to be huge. So then you end up having to parallel caps, and now you're spending a lot of money to get kind of nowhere. We'll kind of see why in a minute. Remember I was talking about that 0 hertz thing? Once you get to that point, if you're within 1 or 2 hertz of 0 hertz, you've pretty much gone as far as you need to go. So that kind of answers that, I hope. So now let's talk a little bit more about this B node here. So we've got a 2K2 and a 33 UF. Now we're going to start playing with these numbers a little bit here to see where we can go with that. So let's say you wanted to drop less volts. Let's say you don't want a 25 volt difference between your screens and your plate, right? So let's drop this down to 1K and we'll recalculate. You'll see here now you only get a 12 volt drop. That's a pretty respectable number. But you'll notice that your 3 dB point went up. So instead of being 2.4 or whatever it was before, now it's 4.8. So you're closer to 5 hertz now. And your attenuation also went down. So you have less attenuation now. So you went from basically 34.8, we'll call it 35, down to 28. So you lost, I don't know, whatever that adds up to. I don't do math in real time. Sorry, not that kind of calculator. So current didn't change. The only thing that we changed was that resistor, and you can see it kind of worked against us. So the only way to repair that is to go double in size. So if you go half in size with one, you got to go double in size with the other. So we went from 2.2K to 1K. So now we would have to go from 33 UF to 66 UF. They don't make 66 UF, but let's just imagine that they did. And now you can see you're pretty much back to where you were. All right, you got roughly 34, a little bit less attenuation, and essentially the same lower point for the cutoff. Let's say you wanted to go with 100 UF right there, and you could in this amplifier. If you wanted to, you could go with 100 UF right there. It would be a ginormous capacitor, so it wouldn't be worth it, but let's say you did. So now you can see here, you went up in attenuation quite a bit, not quite a bit, but a bit. And you went down another dB or so, right? Now you can kind of start to see where that diminishing return is. The resistor actually has more value than you think. So getting the voltage drop is kind of important. It is very important. But let's just say that if you literally only had to drop that 12 volts, that is what you're working with in order to get to a design goal. Now, do remember, I had mentioned it before. What up? Sorry, I'm a little bit behind on things. I'm going to try to keep looking over there. I mentioned before that the ripple attenuation stacks up as you have more and more nodes. So if you have 3 nodes at 37.5 dB, you're going to have much more than 100 dB of attenuation. With this here at 1.59 hertz, you're low enough you don't have to worry about any kind of, ghost noding or any other downsides of lack of filtering, or decoupling as they call it. So let's work ourselves back the other direction. Over here we can see that our final node, our C node, has an 8K2 with the 16 UF, and it's only got 2 tubes on it, and they both are 12AX7s. So we know that they pull about 1 milliamp a piece. So we're going to change this down to 1 each, so 2. We're going to put this to 8.2, and then we're going to go back down to 16 here, and we're going to see what we get. So we drop 16.4 volts. We have 40 dB of additional attenuation, and you can see our low frequency cutoff point has gone even lower than it was before. So we're already getting more and more, reduction or filtering out of, our hertz or whatever you want to call it, almost fully decoupled at this point. So that is this node right here, our C node. And we'll look and see here that we have 335 volts here and 315 volts there. That's a 25 volt difference, if I'm not mistaken. Right? No, 20 volt. My apologies. 15 and 15 is 30, plus 5 is 35. So yeah, we got a 20 volt difference there. So we got 16.4 here. So I think it's actually a little bit more than 2 milliamps that these will actually pull. It might be let's try 2.3. I don't know. 18.9. Ooh, almost. So it's about 2.4. Yeah, about 2.4 milliamps. So they're pulling a little over a milliamp a piece. So these things are working pretty good. Probably due to the fact that it's got that much voltage on the plate. Once you start getting up close to their design limits, they start pulling a little bit more. But you can kind of get the idea. So 2.4, if you want to get that 20 volts out of there. But you'll notice that the other things didn't really change all that much. The current really doesn't affect it quite that much. You're more interested in that voltage drop. But let's say that you wanted to drop even more voltage. Let's go up to 16K. Nah, that's not a common number. We'll do 18K. I think 18.2 is like one of the common numbers. So the same amount of capacitance, and you can see that we've lost 43 volts, so we'd be closer to, I don't know, we'd be just under 300 volts or something like that, right? But our attenuation went up quite a bit. We're almost at 45, call it 47 dB of attenuation, plus that 35 from the first stage. And now you can see here, we're well below that 70 dB goal that we were after. But look at this. We are essentially decoupled completely in terms of filtering on the, HT. So this is really good right here. You can kind of see how you can play around. But let's go one step higher. 16 UF, I don't usually use 16 UF. I usually use 22 at the low end to 30, but I'm going to do 22. And you can see here that we've lost just a little bit more, and we've gone to nearly 50 dB of attenuation. So now we're like, I don't know, 50 plus 35, we're getting closer to the 80 some odd, 85 dB of attenuation or whatever, right? Still a 40 volt drop. What if we went to 30? Almost literally decoupled there. You can see we've climbed up a little bit more. So there's kind of a limit to this, but you can play around. Now let's say you didn't want to drop 43 volts. You wanted to split the difference. So we went from 8 point, so 10. So we're going to drop 5 out of this is 12 point. I can't remember I think it's like 12.7. No, I think it's just 12K. And then you can kind of see how it affects things there. So now you can get closer to 30 volt drop or something like that. Whatever it might be, you can play with this calculator here at antbooks.com to get an idea of how you need to decouple your your filters, your filtering, do all the filtering and stuff like that. The big thing that it will help you with is figuring out your voltage drop. As long as you can guesstimate pretty close how much current draw that you have on that node, and you got to remember that this B node includes everything downstream of it. Same with this A node. It includes everything that's downstream of it. Again, the A node you don't usually factor into your whole number, so this current here, you don't factor the A node into. You're really only worried about everything from the B node down. Now, why is that? I'll show you, actually. I'll show you right meow. So let's just say we put, I don't know what the whole amp has, but let's just say it was 16. But we don't have any resistance, right? If we looked here, there's no resistance in front of this. So we'll put some very low number just to say that we did. So we'll put 0.1K, so that should be 100 ohm, right? It wouldn't matter what size capacitor we use. It's going to be very, very audible. There's almost zero attenuation. There's no voltage drop. And it's well into the audible range. Like we would hear that. So that's why this first capacitor, the reservoir cap, really doesn't factor into your attenuation mathematics and whatnot. You're really only worried about the B, C, D, E, etc. nodes. So do keep that in mind when you're coming up with your things. It wouldn't even matter if this was 100 milliamps. It doesn't really change anything other than the current, which 10 volt drop, whatever, right? But that's with 100 milliamps of current. That's the whole of the amp in this instance here. I believe, I can't remember what this transformer is rated for. I think it's something like, it's right around 100. I think it's like 80 to 100 and something. Depends on which brand you go with. So, anyway, here's another thing to kind of help you convert things around a little bit. Let's say you're trying to convert the lack of decibels into what it actually would equal in voltage. So let's say I put in minus 70 there already, but let's say you only took 10 dB out. That means, relatively speaking, you would have 0.3 volts of ripple. That's one way to look at it from a relative sense, but there's something that's measurable there, right? So 10 dB is not enough loss in attenuation, or not enough loss in ripple to make it go away. That's a measurable amount. Whereas if you go to minus 100 dB, you'd be like, a tenth, a thousandth, whatever of a volt. Like, that's essentially immeasurable. You wouldn't hear it. You wouldn't know that it existed. This thing is essentially a battery at that point, a true B battery, or B cell battery, or whatever you want to call it. I think that kind of just about wraps up what I was going to get at with this episode. I wasn't intending it to be a very long one. I don't know how long we've been on here, but it hasn't been that long, I guess. I got a few of you. Do any of you have any questions that are still here? Did I miss anything, or did I not make something clear enough for you? I hope I made it clear. I know you guys are kind of behind me a little bit too, so I'm going to take another sip of my beer, and I'll give you a chance to respond. Well, I don't see anything from you. So we're just going to kind of call it, I think. We'll just kind of recap a little bit about what we talked about. We'll go back to this view here. So in either case, I botched the beginning. I had tested this thing literally 10 times. That was some great stuff. Yeah, thank you. I appreciate that, Lefty. I was trying to make it better than it was, and I really I'm just disappointed because I really spent some time today to try to make sure the video went off without a hitch, and then as soon as I hit play, shit hit the fan. So sometimes you just win, sometimes you don't. I wanted to do this in live format because it is honestly a little bit easier for me. When I make a video, I have to go back and edit it, and it just turns into a pain in the butt. So, OBS let me down today, darn it. Sometimes you win, sometimes you don't. So in either case, we talked initially at the beginning of the video about how I think Friedman has kind of lost touch with the world. Somebody paid $20 for him to literally say, make pizzas. I cannot believe that. If you missed it, well, you can't miss it because you had to watch the whole video to get through this. I guess to elaborate a little bit more on that, again, going back to this video I made several months ago about, why amp builders are just weird. I kind of, I equated it down to having a cool story, or a story is pretty much the whole of the equation. But I kind of want to say that it's 2 C's. The 2 C's are really what kind of gets you there: competence and confidence. And you're probably wondering how having more than enough competence doesn't make up for a lack of confidence. And it's really simple. Whether you think you can or whether you think you can't, you are right. And it's very, very true. Oh, no, I know, dude. Lefty, no, it's fine. I'm not really looking for viewers necessarily, or subs and all that stuff. I'd love to get more subs. That would be helpful. But the challenge I'm having more these days is just the drive to make these videos. You probably noticed that I went through several months where I didn't really make anything. And it was just because this is kind of a burden for me. Like, I work during the day. Yeah, no, check it out from the beginning, my man. I was trying to recap it a little bit, but I didn't want to, turn into a record player too much. But I already do bad enough as it is with that. But making these videos is a pain in the butt, so I wanted to just try to make it easier on myself. So I'm trying to make OBS work for me a little bit, and I'm trying to get the quality up. So I finally got another 4K. I got a 4K camera that works with this kind of setup here, as opposed to my iPhone, and it's already making everything being done in real time much easier, but it's prone to failure apparently. As we're finding out, I got to figure out why it did that. So in either case, 2 C's I was getting at. So whether you think you can or whether you think you can't, you are right? So it doesn't matter. I usually relate that to motorcycles, especially. I was this close to getting into racing motorcycles, and I decided against it mainly because I knew it was just going to probably kill me. Once I see red, it's game over. I'll do whatever the guy in front of me is doing and then try to do that extra inch more. And going with the 2 C's there that I was talking about, when your ambition outweighs your ability, you start running into problems. So that's kind of the whole thing with this 2 C's that I talk about: confidence and competence. If you're going into a corner at 100 miles an hour, it doesn't matter if you could do it with your eyes closed and a hand tied behind your back. If all of a sudden you start to believe that you can't do it, you're probably not going to do it. Conversely, if you have an overt amount of confidence, but not nearly enough confidence or competence, that's why it's hard to do this sometimes, but you know what I mean? Obviously, if you're going into the corner thinking, oh, I got this, no big deal, but you can't actually do it, then you're going to eat shit too. So those sort of things there, I kind of feel also add up to the building of an amplifier and doing it well. Whether you think you can or you think you can't, you're right. So you just have to do it, and eventually you'll get comfortable with it, and you'll just be able to do it. Now, the biggest, I think, disconnect for most people is understanding what this is. They look at this and it just looks like a bunch of line and squiggly lines and these weird little separators here that have silly numbers on them that don't mean anything. If you keep reading this stuff here, eventually you're going to be able to look at this and it'll just make sense to you exactly what it is and exactly how it works. And then some of the other things that involve the math, such as, dealing with the power supply and stuff like that, all of that stuff will just kind of start to click. And you can almost do it in your sleep. You'll start coming up with these ideas like, okay, well, what if I did this? And if you go back to some of my earlier videos, I talk about the typical range that most of this stuff exists in. There's pretty much a range for everything. There's no reinventing the wheel for guitar amplifiers. Nobody's doing anything all that different than the last guy did. Somebody else has already done it, for sure. They might have done it in a slightly different way, but in essence, somebody else has already done it Whether or not it's been popularized or not is up for debate. Not everything you do is going to sound good, obviously, so that's why you get back into things. But if you look on the interweb and you go through enough schematics, you're going to start to see that they all kind of have the same kind of things going for them. There's only so many different ways. Yeah, you gotta go through it, my man. I know it's kind of long. I go on for quite some time on some of this stuff, but I get tired of listening to myself too. But that's why they created the arrow button, so you can just forward through everything real quick. Just get to the part that you want, right? But you'll start to see that they all kind of have this similarity to them. You know, there's only so many different ways you can do the power supply. That's probably going to be the most common thing between all of them, is going to be the power supply. Once you get through all the weird crap that they do for the safety aspect of it, maybe they, I'm not going to pull it up right now, but when I did the Champers videos, I showed the original one, and they had like the bridge, a full wave bridge rectifier, and then they put these capacitors around each one of the diodes. They did that to abate on noise. The problem was they're trying to get rid of noise in the wrong spot. But it was easier and cheaper to do that than it was to do it the other way, which might have cost more money. Right? When you take 4 cents worth of parts and put it around 4 cents worth of other parts, like you literally only have 8 cents invested. Whereas if you go another direction that costs, $1 for, the one thing that makes it all work better, which way are you going to go when you're a bean counter? You're going to say, well, put these 8 cents worth of parts in there, not the $1 one. It's literally that. That's what separates the men from the boys. But yeah, you'll start to see through all that kind of crap, and then it'll just start making sense to you. You'll understand what the G2 is and how it relates to a screen on your power tubes. Pentodes are all kind of the same. All power tubes are pretty much the same. The pinout might be different, and there's some slight differences between them on the internal connections and the external connections. But for the most part, a pentode is a pentode. There's 5 parts to it, and generally you only connect to 3 or 4 of them, because a lot of them are internal. So this here is another grid. I think they call it a G3. Maybe they call it something else. I can't remember off the top of my head, but it's attached internally to the cathode. You don't have to deal with that connection. Now, maybe once upon a time in the days of yore, when they were first making these things, you had to make that connection, but then they're like, why can't we just do it in the tube? And then they started to do that. You'll probably see that any amp that has EL34s in it, that they connect pins 1 and 8 together, which is the cathode, and I can't remember what the other pin does, but it's probably this one here in that tube. Whatever. I can't remember off the top of my head what that particular screen is called, but in either case, maybe you still have to do that because they couldn't do it, in the tube itself. Whatever. But most all power tubes have at least a grid, a plate, a cathode, and 1 or if not 2 grids that you will connect to. 9 times out of 10. A/Tech. That's right. Thank you, my man. Good to see you again. I'm glad to see you guys all left Andy Lederman's thing he was doing. Like, dude, what was that thing he was doing, the live mod? Was that like a 6 or 7 hour long live feed? That dude's a freaking beast when it comes to that stuff, man. I don't love the sound of my own voice enough to talk that much. I'm not saying that he does either, but that dude's a beast sometimes. I couldn't do that. I think I've already gone on too long. I'm just trying to tie a bunch of my other videos together into this one episode here, just so I don't have to do other videos about it later. Because if you've made it this far, you are a super trooper. And I see that there's now, of course, more of you. 11 hours? Holy hell. That is insane. I was able to watch part of it during my lunch period today. I took a little break and turned on YouTube, and I saw you had a thing. I have a different account that I use at work. It's actually my name, so it's Luke. If you ever see Luke on there, you'll know who I am. But I was trying to help a little bit when his thing started going up in smoke and other stuff like that. I don't think he realized it was me though. I imagine he's probably asleep by now, so he's not in the chat. Well, shoot, I wish you guys were all here earlier. We could have really gone through some more Q&A, but again, if you have any questions, let me know. But anyway, as I was getting at it, you'll be able to see these in your head, and it'll just start to make sense. It'll just click. Obviously, you'll start to see some commonalities as well, like 100 ohm screen grids, like that. You see that all over any kind of amp that has a screen grid resistor. Is that the ideal value to put there? Probably not, but 9 out of 10 amps from the days of yore used 100 ohm. Why? I don't know. Probably because it was cheaper. Maybe they anticipated it as being the safety fuse or something for the screen grids to help protect the amp. Who knows? It's impossible to get in their minds. But again, when it comes to 12AX7s, there's just, again, certain values. They all kind of just do the thing. Let's talk about the phase inverter a little bit right here, because there are some differences in this one than you will see in a like a Fender style one. First and foremost, you'll notice that they got 470 Ks as opposed to the normal 1 megs. What I can tell you is, hold on. Excuse me. I had to get my gratuitous burp out for you. Wouldn't be a show with A-Tech if you didn't get burped on. I'm sorry. That was rude. My apologies. Thank you for sticking with me if you have so far. And now we've got 6 viewers. Darn it. Where were you freaking 20, 30 minutes ago? Anyway, you don't see that value very often, much below 1 meg. And what I can tell you is that it's not super duper important what value you put there. It just has to be there. 470 will lower the overall amount of bass that the phase inverter will produce. But it's not like a marked difference. You're not going to go from just butt tons of bass to no bass at all. You're going to go from butt tons of bass down to a little bit less of butt ton worth of bass, assuming that's how much bass is coming out of there. Conversely, again, you don't go much higher than 1 meg. There might be some other designs out there that kind of breach that a little bit. You can use different values for each one. So if you're into that kind of thing, I think Friedman actually does have a design where he puts like 1 meg in one and 470 in another or something like that. You can use it to try to balance things a little bit in there. It does do a thing. The size of this, it's not a coupling cap, but it's kind of more or less a bypass cap, if you will. But it's used to connect to the second grid to ground. You do have to have this if you're only using one input on your phase inverter. But the size of that cap does determine the overall amount of bass. So if you go really small, kind of similar in size to this, it's, again, not a marked difference, but it does make a difference. My finding with it is that when you go with larger values, it should be about 10x whatever your other channel is. So if your primary channel, again, assuming that you're going with only one input of your phase inverter, and you're going with a 10 in, you would go with a 100 in. You're supposed to go 10x. Now that's not always practical and doesn't always make sense. So 0.047 would be fine. 0.022 would be fine. 0.01 would probably be fine as well, even though this one here is a 0.001 or something like that, if I'm not mistaken. So this is something you can play with. The tail resistor, a lot of people don't play around with that. They don't understand really what it does. In an amp like this, the tail resistor is kind of important. The smaller it is, the more drive it'll put on your output tubes. And the more drive you put on your output tubes, the more likely with an EL84 for them to start getting fizzy and just literally annihilated by the amount of gain that's coming out of this guy here. Whereas if you go larger in value, so 47K, let's say 52K, 68K, you can go as high as you want, pretty much. But what it does is it takes more of the onus from the power tubes and moves it to the phase inverter. So now the phase inverter will break up much sooner, and it'll leave the power tubes alone a little longer. So there's, again, a point of diminishing returns, a balance. And then these guys right here, the grid leaks for the power tubes. It's equally as important in a cathode biased amp such as this one as it is in a fixed bias amp. Most people break the rules. If you look at the tube data sheets for like EL84s, EL34s, 606, etc., etc., there's pretty much two standard values that are there. For EL84s, because of the way that they work, they are a little more sensitive, and they also allow for up to 1 meg, so 1 mega ohm of grid to ground reference. And that literally means your grid, this one right here, the pin 2 that we're looking at here with that 8K2 on it, that 8K2 plus 470K cannot be more than 1 meg with a cathode biased amp. If this were fixed bias, it could not be more than 500K. Now with most large bottle glass, so we're talking 6v6 all the way up to 6550s, etc., etc. So that includes the L34s and 6L6s. The grid to ground volt or reference or resistance that you're allowed to have cannot exceed 500K. So that's why you generally see 220 to 100K in the larger bottle glass tubes out there. So again, just little things like that. You'll just start to see all that stuff, and it'll make sense once you kind of figure out what it's for. These are grid leaks. They do exactly what they say they do. They leak signal off the grid. So the smaller this value is, the less voltage we'll get on the grid. Makes sense, right? So it's another place that you can use to tune your amp, and it kind of is, in a way, works like a limiter for the power section, if you will. Now, there is a practical limit to how low you can go, because if you go much lower than, say, 100K, obviously you just kind of get the tubes into shut off or cut off all the time. More or less, they're so close to being turned off anyway that they're not doing anything anymore, relatively speaking. So, but you'll notice here that they got a pretty small value here. It's a 0.01. That was a 0.01 over here too, yeah. So 0.01. It works in conjunction with that. It creates a low cut filter, if you will. So the lower you go with this, the more bass will roll off. And that's why you'll notice in some Marshall designs, when they had a 220, they went with like a 0.047 or a 0.1 or something like that. Or no, excuse me, the other way around. They had 100K at one point, and they went with a 0.1 UF. But a 0.1 UF made it a little too woolly. So then they went the other way. So they went with the 0.022 UF to get some of the bass out, but in order to make it not too thin, they ended up going up with grid stopper value, or grid leak value, excuse me, to 220. There is a problem with that though. So the tubes work in parallel with each other. So in this case, there's one to one, so you don't have to worry about that. But if you're sharing two tubes, this value is doubled. So it's 500K for both tubes, and it looks to the tubes as if it's 1 meg, right? That's how you would look at it. If you had 4 EL84s in here, this would look like to those two tubes there as if it were 1 meg. That's where they start getting into trouble with these 4 tube amplifiers, or 4 output tube amplifiers. Is they neglect that number a little bit. So with 220K in that position, plus the grid stopper, if you have a 5.6K grid stopper, as far as those two tubes are concerned, you're right at that 500K limit that they have. That's not a good thing, by the way. If that number is too high, if it gets too, let's say you did go up to, let's say 680K or something like that, it could cause the tubes to go into runaway, or bias runaway, I should say. There is a way for it to do it. I don't know all the exact details of it, but just know that that is a thing. Don't do it. But so we've kind of went well beyond the whole HT supply sort of thing, but let's kind of recap back on the actual thing of topic. Again, first cap in a power supply is the reservoir cap. It is designed to just store energy and help do this portion of the whole job, which is to fill that gap that falls down towards zero. That's what its job is to do. The second stage is where most all of the filtration occurs. And you've seen that already before when we did the math here, where we took this 2.2K and our 33 UF with our 12 whatever of whatever. You can see we got 35 dB of attenuation. We've got a 26 volt drop, and we're down to 2 hertz essentially worth of, filtration. Right? So you know that now, that this is where a large portion of the filtration starts. Where it ends is over here. The more nodes you have, the more filtering you have, which means the more decoupling you have, which means the more attenuation you will have. The more attenuation you have, the better. As a design goal, below 70. You're looking for at least 70 dB of attenuation, and it stacks for every node. So if you have 10 dB here, 10 dB here, 10 dB here, that's 30 dB, right? Let's keep doing the math on it. So if it was 20 here and 20 here and 20 here, it's 24, you would have 60 dB. So objectively, for any one node, you're trying to shoot for right around 30 dB. I went over this obviously earlier. I'm just kind of recapping on things. I'm trying to get some mileage out of this. I'm still so very angry at myself for my faux pas earlier. It just bothers me. Anyway. So, and then again, these two values or these two parts work in conjunction with each other. So, if you go half the size in one, you have to go double the size in the other to get the same relative amount of ripple attenuation and hertz, filtration. So if you go with a 1K1 here, or 1K, you need to go to 66 here in order to maintain this same level of attenuation and low frequency cutoff. But your voltage will change if you change just the resistor. So do remember that the resistor sets your voltage drop for each node. And that's what limits you on what you can do for the UF or the capacitance. If you know that you want 20 volts of drop and you must have that 20 volts of drop, that is going to be what determines the size of this resistor that you can use. If you know that you've got two 12AX7s, there will be 2 milliamps of current, roughly. You punch that into this thing here, and you can kind of see what that would result in. So let's put the 8.2 in there, and we'll keep it, and we'll put what they had in there. We'll put the 16. So you can see here what you get with that. Well, you can go higher in attenuation or in UF if you want. So you can go to 33. That's not a problem. You're just going to get more attenuation and closer to full, isolation or full decoupling. All right, so you know that. But let's say you need more or less voltage. Well, that's going to be determined by the size of your resistor. If you put a 12K resistor in there, you're going to get more of a voltage drop, so you'll lose more voltage. But it's usually not a problem if you go larger in resistor. It's usually a problem if you go lower in resistor. Having more ripple attenuation and filtering in the the hertz or decoupling from hertz or whatever, not so much of a problem. But if you know that you only need a 10 volt drop, that's where you're going to run into problems, because you're going to put like a 5K in there. I got that one, banged it. So yeah, you put a 5K resistor in there to get your 10 volt drop, but then your attenuation changes a little bit, especially if you're using a lower capacitor. So you can see here, it doesn't really add up much. You're still going to get your 70 volts roughly worth of attenuation, but you're still sitting right around 2 hertz. Again, close enough that you'll never have any problems with this. But the closer to 0 you can get it, the better. That's all. So in either case, I hope this answers some questions. I want to thank you all so very much for sticking with me. I'm going to call it a night, and we will, we'll see you guys all on the next one. Take care. Goodbye. And that one.